Qt-Modeler offers a handful of communications analysis tools that, combined with high-resolution terrain data, gives users the ability to pre-plan the placement of antennas and evaluate obstructions to communications propagation. It's important to note that Qt-Modeler's tools will focus on line-of-sight communication, which is where the transmitting antenna needs to actually see the receiving antenna and vice versa. This is not a full RF propagation tool, and so therefore we will focus on line-of-sight communications like microwave and satellite communications. The first tool we'll look at is the horizon analysis tool. This tool requires a marker to be placed in the scene, and this marker represents an antenna that you may be thinking about placing on the ground in this area. Once the marker is placed, right-click on the marker in the layer tree, go to Analysis and Horizon Analysis. This chart opens up, and the first thing to note is the slider on the bottom. As you slide this left and right, we see the azimuth and elevation of the angle to the object on the horizon. Azimuth and elevation is a very common way to express pointing angles for satellite antennas. As you move the slider, you also see a vector in the scene, and that's indicating where in the scene this particular azimuth and elevation is, and what is the object that defines the horizon. One of the most common uses for this tool is to determine if this antenna has visibility to satellites, and if there is any obstruction in between the antenna and the satellites. The most common satellites will be geostationary satellites that orbit around the equator of the Earth. These satellites and that band are represented by this green arc, which is also called the Clark belt. There's a button here to turn this on and off. So what I can see from this chart is that the Clark belt is above the building, i.e. above the horizon, and therefore this antenna does have visibility to all of those satellites. In contrast, if I were to reposition this antenna much closer to the building, particularly when the building is to the south of the antenna, I move the marker, I have to click Recalculate here, and now I see that the Clark belt is blocked by this arena, and therefore, at least in this section, I do not have visibility to the satellite. So let's move the antenna back to a more sensible position. Hold down K, drag, move the antenna back, recalculate. If the satellite I want to look at is not in the Clark belt, I need to add its position as a POI, a point of interest. Click the Add POI button and put the azimuth and elevation of that pointing angle to that POI. So let's call it Sat1. And the azimuth is 205 degrees and the elevation is 14.5. Click OK. And here's Sat1 in the chart, and that tells me that Sat1 is up above the horizon. I'll swing the arc over to it. And I can also show the POI vector. So as I move through in the 3D scene, I can see the look angle, the pointing angle to that satellite, and see that it's free and clear, and there's nothing on the horizon blocking my visibility. So a couple of settings worth thinking about. First, curvature of the Earth correction. If the distances get very far, meaning more than 5 kilometers or so, you may want to correct for the Earth curvature and click Recalculate. And if you want to put the antenna on a pedestal or elevate the antenna in some way, you may want to put, for example, 2 meters and then recalculate. The radius is how far out the vector goes. So if you want it to go out only 500 meters, then just type 500 and recalculate. And now the vectors are much shorter. You can export the horizon 2 ways. 1, as a picture to PowerPoint, and 2, as a numeric chart, clicking the Export Horizon button. you get a CSV file with 3 columns: azimuth, elevation, and range. And that's every ½ degree on the azimuth, the elevation of the horizon, and the range out to that object. The next communications tool is the sensor cone. It's a more visual tool, and it is also attached to a marker. Let's right-click on our marker. This time we'll go to Shapes, Add Sensor Cone. The initial cone will be pointed straight up with an angular spread of 45 degrees. So the steps in this tool are to narrow down the field of view or the cone spread. I'm entering 10, click Apply. And now it's just a matter of setting the direction or orientation of the cone. So you can use a slider to bring the cone direction down, and then also the slider to set the heading. So this is a more visual representation of sensor coverage. This will be equally useful for a sensor such as a video camera. And one thing you might want to add to this is an AGL value to the marker, or above ground level. You can see that this cone is originating from the ground level. So let's right-click on the marker, edit, and add an AGL value. Just say 2 meters. Apply. And now the center of the cone is 2 meters off the ground. So this is a great way to just visually inspect the coverage of an antenna or a sensor. Here's a little pro tip on the sensor cone. You can attach it to an aircraft. Place a marker, open the Edit Marker window, attach an object. Here I've attached a UH-60 to the marker, give it an AGL value. Here I've added a 40 meter above ground level value. And now attach a sensor cone. You can do that from this window as well as from the right click over here. Edit the cone and just direct the cone downwards with the pitch at 132 degrees there. And now as you move the marker around with your normal K-drag, you can see coverage, sensor coverage from the aircraft. The next kind of communications analysis is sensor model line of sight. So this is just a variant of regular line of sight in which we attach a sensor to the marker itself. Very similar to the sensor cone, but this will give a more quantitative and exportable result. Place your marker. Here I put the antenna on the corner of the building. Add a sensor, right-click on it in the layer tree, go to the Edit window, check the Sensor FOV, field of view, and then let's edit that sensor. Click the Edit Sensor. I defined a field of view at 20 degrees, pointing south 180 degrees, and just slightly below horizontal. Let's turn on our virtual line of sight map now. Right-click on your marker one more time, Analysis, Virtual LOS Map, activate. Let's close this out. And now the green is the coverage from that sensor at that field of view and that angle. You can go in and edit that now. You can rotate it around or lift it up or tilt it down. Once you're happy with the settings and the pointing of the sensor, you can do a traditional line of sight now and have a raster result that you can export. Click your line of sight button, choose the antenna 2. I'm going to turn my not evaluated color to white and then just apply. So it may be hard to see from the zoomed out perspective, but when we zoom in, we have a line of sight result that represents the coverage of that sensor. And that could be, again, a camera or an antenna. And this is its coverage in the scene. Once you have that, you will have your vertex colors, which you can export like any other line of sight result. Another tool that can be used for communications analysis is vector line of sight. The hotkey for vector line of sight is L. So just put your cursor somewhere, type L, and you'll get a red or green vector to all the visible markers in the terrain. In this case, the markers represent antennas, and the green vector means that there's visibility. And in a visual sense, that means line of sight. These can see each other, but in a communication sense, it means the antennas can see each other. Hold down L and move through the scene down the street, and we can see the differing vectors as different antennas come into and out of the field of view. This can also simulate an airborne platform. Right-click on the button and give the observer height an AGL value of, say, 30 meters. And now the OP is flying through the scene and looking for visibility to the same antennas. To get rid of the vectors, type L again. So those are some of QT Modeler's tools that can be used for communications analysis. The horizon analysis, the sensor cone, the sensor model line of sight, and vector line of sight. Keep in mind that these are all line of sight tools for the most part, and it aids in evaluation of line of sight type communications, like microwave, like satellite communications. Please let us know if you have any questions.